Okay, good afternoon, class. This is Group 8, and we'll be talking about multiplexing. Bear with me, this topic is very short, but I'll try to get through it as well as I can. Now, multiplexing is the process of combining signals from multiple sources for transmission across a single link. So as you can see in the picture here, you have a number of inputs, and they're all channeled through a single link. Now, here are some terms that I want you to be familiar with. A path refers to the physical link. Channel is a portion of the path that carries a transmission between a given pair of devices. Now, you want to know why do we need multiplexing? What is it all about? And you know what's the use? So, transmission nowadays can be very expensive. So, by using multiplexing and compression techniques, you can save a lot of money, or the business can save a lot of money. As the data capacity of the lines increases, it will become more and more cost effective. So basically, applying multiplexing can really save you a lot of money, and it can save you on a lot of resources. Now here are some of the categories of multiplexing. We have frequency division multiplexing, FDM, wave division multiplexing, WDM, time division multiplexing, TDM, synchronous TDM, and asynchronous TDM. Now, I'll leave it to my group mates to discuss the rest of these. Thank you.
Hi, I'm Jobs Michael So, and I will be discussing frequency division multiplexing. Frequency division multiplexing is an analog technique that can be applied when the bandwidth of the link is greater than the combined bandwidth of the signals to be transmitted. Now, common examples of frequency division multiplexings are radios and television broadcasting and the telephone systems. Basic concepts. The signals generated by each sending device modulate a different carrier frequency. The modulated signals are combined to a single composite signal that can be transported by the link. Carrier frequencies are separated by enough bandwidth to accommodate the modulated signal. The bandwidth ranges are the channels where the various signals travel. Channels are separated by strips of unused bandwidth to prevent signals from overlapping. These unused bandwidth are commonly called as the guard band. FDM process. Each telephone generates a signal of similar frequency range. The multiplexer modulates these similar signals to different carrier frequencies. Resulting modulated signals are combined into a single composite signal that is sent out over the major link. So after the multiplexing process, there is the demultiplexing process that will take place on the other side, so that the signals that are combined can be separated once more and then transmitted to the right frequencies. It will be discussed by my next groupmate. That will be all.
Demultiplexing uses a set of filters to decompose the multiplex signal into its constituent signals. Signals are passed to a demodulator that separates them from their carriers and passes them to the waiting receivers. It is the reverse of multiplexing. The multiplexers are used to connect a single source to multiple destinations. This process is the reverse of multiplexing, as mentioned previously. It is used mostly at the receivers. It has many applications. It is used in receivers in the communication systems. It is used in arithmetic and logical unit in computers to supply power and to pass on communications. The multiplexers are used as serial to parallel converters. The serial data is given as input to the multiplexer at regular interval, and the counter is attached to it to control the output of the demultiplexer. Both the both the demultiplexers and multiplexers play an important role in communication systems, both at the transmitter and receiver sections.
So the topic is for FDM analog hierarchy. So as you can see, you have the hierarchical system. So you have the multiplex level, you have the group, supergroup, master group, and jumbo group mix. Actually, there's another group and so on as the number of voice channels increase. So for the group, you have a 12 voice channels, supergroup you have 60 and so on, with also increasing frequency and formation. So for you to easily understand this, we have the FDM analog hierarchy. This is the figure. So you have 12 voice channels here for the basic group, and then the super group. So you have a 60 total voice channels, and so on. So the next one is the wave division multiplexing. So it's also like FDM conceptually, but it uses light. Yes, uses multiple beams of light at different frequency. Also, it has an optical fiber as the medium. Each color of light or wavelength carries separate data channels. Commercial systems of 160 channels of 10 Gbps now available. So you have a light in the middle to send your data in different wavelengths, of course, as light has provides different wavelengths for every color. So it's like that. So you have a data that will be transmitted in different colors, and will be combined into a single white light using the prism principle. And then in the demultiplexer, it will be again so the wavelength division multiplexing has many different applications used in satellite communications and tactical internet working, telemedicine and video conferencing, and also military applications. So the last one is the time division multiplexing. It's a technique of combining signals from a low speed channel to share path on a high speed channel. So it's just like the same with others. For now, for the time division multiplexing, it uses a equal time interval to send data. So you have the multiplexer here and the demultiplexer. So first, you will send data from A, then at equal time interval, you will also send data for B and C. So time division multiplexing was first developed for applications in telegraphy to route multiple transmissions simultaneously over a single transmission line in the 1870s. But it gains popularity in digital telepathy in the late 20th century. So this is the difference between time division multiplexing and wavelength division multiplexing. So both share um, high speed medium in the middle like optic fiber.
Chapter 8.3 Introduction to Pulse Modulation. So, pulse modulation is the process of converting the analog signal into digital pulses. So, under pulse modulation, we have two different techniques, namely the analog pulse modulation and the digital pulse modulation. Under the analog pulse modulation, we have the first type, which is the pulse amplitude modulation, or the PAM. In here, the signal is sampled at regular intervals such that each sample is proportional to the amplitude of the signal at the sampling instant. Here is the graph of the PAM. Next is the pulse width modulation, or the PWM. In this type, the amplitude is maintained constant, but the duration or length or width of each pulse is varied in accordance with instantaneous value of the analog signal. Next is the pulse position modulation or PPM. In this type, the sampled waveform has fixed amplitude and width, whereas the position of each pulse is varied per instantaneous value of the analog signal. The next type of pulse modulation, which is the digital pulse modulation, we have a type under it, the pulse code modulation or the PCM. The analog signal is sampled and converted to a fixed length serial binary number for transmission 1 and 0. So here is the comparison between the above modulation processes of different analog modulation, PAM, PWM, and PPM.